Hello, everybody. Thanks for the introduction, and thanks to Adrian and the AtoCube NeoSpec team to bringing us once more together, this growing field of s-SNOM users. So I'm really glad to be back here. And yeah, I want to talk about infrared phonon polaritons and terahertz plasmon polaritons, two topics that are briefly outlined here. So you heard a lot about phonon polaritons, but typically, or at least so far, these polaritons are used and observed in exfoliated hexagonal boron nitride or other 2D materials. Now, if one wants to go in the future to real-world applications, then this is not really very useful. So we should look for phonon polaritons also in CVD-grown material. And so we looked very long for material, and actually we got some really nice CVD-grown material from Andrea Ferrari's group within the flagship collaboration. And I will, in the first part of the talk about these polaritons that you can see here already. Looks unusual, but I will explain you what it is. Then in the second part of the talk, I want to switch to terahertz, to plasmons, and actually to a 3D material. So actually, we don't need necessarily 2D materials to see ultra-confined polaritons and anisotropic ones. So we found, by chance, actually silver telluride, which is a monoclinic material, polaritons that propagate in different directions with different wavelengths. Actually, it's a monoclinic system. We should have expected the so-called shear polaritons, but we didn't find them, and I also will explain you why. So I skip most of the introduction because we all know in the meantime what polaritons are and how they can be imaged. So just focus here on some work that we did on hexagonal boron nitride, exfoliated flakes. The first ones who saw them were actually in Dimitri Vaso's group. We followed this work rather quickly, and we found here, for example, that also along edges, one can have modes. Actually, if you have a closer look here, they have a different wavelengths. These are so-called edge modes in comparison to these slab modes. They're more confined. So this is nice because these edge modes, they can actually propagate when, in case we make very narrow waveguides, these modes can hybridize in opposing edges, and they can give rise to waveguide modes that are unlimited in the width, so we don't have a cutoff. So these modes that you can see here actually are cutoff limited, so if you make a ribbon, as the ones that you can see here, this mode would not propagate, they would have a cutoff the same way as a dielectric waveguide mode would have. But these edge modes, if they're hybridized in opposing edges, they can propagate even in principle in 1 nanometer thin layers, ribbons. So that's nice. Now, that one could use for transporting phonon polaritons, but if you truncate them, then we could make linear Fabry-Perot resonators, because now the phonon polariton launched by the tip is bouncing forth and back, and that gives rise to these phonon polariton Fabry-Perot resonances. I will come back to this in a second, what we can do with that. And another thing is, what we did some while ago, we can use this, in principle, in-plane isotropic HBN when we can structure it, and then we can make artificial hyperbolic meta-surfaces out of that. So what you see here is an antenna on top of a grating, and that launches waves. And as you can see, these waves have tilted wavefronts, the same way as what you see in molybdenum trioxide. The difference is here we break the in-plane symmetry by structuring that. And so now we have an effective epsilon, or permittivity, that is different here than here. And so we can make hyperbolic metasurfaces artificially. That's, of course, quite challenging. You may not see that. That's a grating with the 20 nanometer gaps, really hard to fabricate. And so now with the upcoming in-plane anisotropic materials, such as molybdenum trioxide, people focused more on these natural materials because they're much easier to handle. So, nevertheless, what we are working quite a bit is we try to couple molecules with these enhanced polaritonic fields. The first idea was to do sensing, similar to surface-enhanced infrared absorption spectroscopy. So we made ribbons, and we have now transverse Fabry-Perot resonances. And you can see here this phonon polariton Fabry-Perot resonance, how it shifts to smaller frequencies if we change the widths here. So that is change of widths. So these are really deep subwavelength scale infrared resonators. And now if we evaporate, in this case, CVP molecules, is a semiconducting organic molecule, then we see here actually, so these are the same ribbons, and now with molecules, and then we can see that once we match the cavity resonance or the ribbon resonance with the molecule, we get here even into the strong coupling regime. That was unexpected. So we can achieve that with a few molecules. 30 nanometer, and we calculate actually that one could do that eventually even down to the monolayer level. So seeing a vibrational strong coupling with really few molecule sensitivity. So I don't talk about strong coupling, we did quite a bit on that. What I want to focus now is a little bit the idea of using CVD-grown hexagonal boron nitride, because making real-world devices for sensing, exfoliating and fabricating is not really something that is very practical, so we would need CVD-grown material. And as I said, we screened a lot of materials, and finally we got something from Andrea Ferrari's group within the flagship proposal. And you can see here a light microscope photograph, actually, of a 1 centimeter substrate, and you see here different layers. So that's not monolayer CVD-grown graphene, hexagonal boron nitride. This is multi-layer material, 6 nanometer thick. And then we can fold it and stack it on top of each other, and we can create that way. We can tune the thickness just by stacking them on top of each other. And these are 4 layers that are stacked on top of each other. You see here the topography image, and that's the SNOM image. If you look at, let's focus on the edges first. If you average along this edge here, we see the typical fringes that are due to tip-launched polaritons that are back reflected at the edge here. That is nice. We can actually fit them, and then we can derive the dispersion, here the data points, and then compare that with a simulation of the polariton dispersion, for which we used a far-field measurement to derive the dielectric function of exactly this material. And that fits very nicely here. So we definitely see phonon-polaritons. But we see another thing, namely that in the center here, we see a lot of strange patterns. So what is that? Is that inhomogeneities? Is this a variation of permittivity, or is it polaritons? So that was unclear at this moment. We see that the kind of periodicity of this random pattern changes, so it indicates already this may be polaritons, but where they're coming from. So to learn more about that, we did TEM. And in this TEM image, we see that this is polycrystalline material. We see here the rings that shows already that they are eventually tilted. We also see moire patterns here. So that all indicates that there are a lot of defects in the material. Also, it's a single crystalline. It's crystalline material, but it's polycrystalline, not a single crystal. So to learn more about that, we looked at a much thinner layer, and we see that these fringes become narrower, so that looks good. And we also see that this pattern here actually changes, which is another indication that these are polaritons. Now, in order to analyze them, what we did is we just took this inner part of the image and we Fourier transformed it in 2D. And these are the Fourier transforms. And what we can see here are rings. So we have a defined momentum in all directions. In all directions, it's the same. And so now by analyzing that, so we developed some theory to fit these Fourier transforms, and from that we can get then a dispersion, and this dispersion again for different thicknesses we get the dispersion, and this dispersion fits perfectly with the simulated dispersion here in the lines. So that means simply that also we have really high quality HBN that supports these phonon-polaritons. We have a large amount of defects in which these polaritons scatter randomly. And so now we made a simulation to confirm it further. So we simulated a slab, and then we just put some holes in the simulation in there in a density that is comparable to what we see here. And you can barely distinguish the experiment here from the simulation. That's the Fourier transform, so all matches perfectly well together. So that means we have a CVD-grown HBN that we can stack. We can make that even 50 nanometer thick. We have phonon-polaritons. All is nice. But of course, if you're, let's say, interested in guiding light or making fancy optics, it's probably not very useful because these polaritons, they scatter everywhere. So is that useful? Not for these type of applications, but we are anyway interested eventually in ribbons and resonators. And so what we did is we fabricated ribbons of different widths. You can see them here. So we did a far-field experiment here on the left side. And we did reflection spectroscopy, and these are the experimental data, these are the simulated data, and we see very nicely these resonances in these ribbons that again shift to higher frequencies if the ribbon width is changed here. Now to see what is the mode, we took the SNOM and then we imaged these ribbons. That's the topography here, and these are the images, these are the amplitude images, and what we see here are the strong fields at the very edges here, which indicates that this is a fundamental dipolar resonance in these ribbons here. So you can see here, that's a cross-section. You see here, that's topography, and at the edges, we see these high fields. Now we did a simulation. Here you see an individual ribbon, and we can see here that's the real part of the electric field, and we see strong field concentration on the left and right side. So that's a dipolar resonance, and that works very nicely. And so what about the quality factors? Well, the theoretical quality factor would be this line here, 75, which is, well, not bad actually. Compared to plasmonic resonators, it's pretty good. This is what we get from the simulations, and here the green data points are the data that we extract from these measurements here. So they're a little bit lower than the expected ones, but this we attribute simply to these rough edges here that we create through the etching. So quality factors of around 50, as I said, this is pretty good. Compared to plasmons, that's even better. So next step would be to do the whole thing with molecules for sensing. So that could be an interesting step towards, let's say, large-scale phononic resonators. And we used such resonators already for gas sensing, CO2 gas sensing, and there's a couple of more things with which I cannot talk at the moment. And so, yeah, that's potentially interesting. And with the s-SNOM, actually, we could learn a lot about the materials. We can not only study polaritons, but we can eventually also use that to learn maybe about defect distribution and so on. Good. Now, second topic, we switch gear now completely. As I said, we go to plasmons, we go to terahertz, and we go to 3D material. And the main focus here is this anisotropy. And I just have this slide that summarizes a little bit what we heard the last days. This is all phonon polaritons. I showed you that we created artificially a hyperbolic metasurface out of HBN. But then lately afterwards, MOS3 came up, which is naturally in-plane elliptic or hyperbolic, depending where we look. And so here we made a disk, and then we see that in the Fourier transform, these fringes appear as either elliptical iso-frequency surfaces or hyperbolic ones. So we can tune here between the two. And then twisting gives rise to interesting phenomena if you twist two of these anisotropic materials. And well, I don't want to talk about that because people talked about it already. The point here is that these are all phonon polaritons. And phonon polaritons are great because they have very long lifetimes, up to 10 picoseconds or more. The problem is, however, they are barely tunable, so we cannot gate whatever HBN and then change the dispersion like we can do for example, with graphene. And they exist only in very narrow ranges, the so-called restaurant bands, which are typically in between, well, mid-infrared and far infrared. So at low terahertz frequencies, they're much harder to find. They also don't exist at visible frequencies. So, but we find them in a variety of materials. Now, what is much less explored are plasmon polaritons. First of all, plasmon polaritons generally in 2D materials have not been widely studied, but anisotropic ones are even harder to find. Pros would be we can dope semiconductors, and then with that we could tune the plasma frequency, eventually even via gating. They exist in principle up to visible frequencies. And actually, it's just on the archive, very beautiful work where they see anisotropic plasmon polaritons at visible frequencies, actually. The problem is they have a short lifetime, so that's a little bit the problem. So we were looking for that, but actually I found by chance this paper here from Faixiang Shu's group at Fudan University. That's a pure transport paper, and they report here silver telluride is a monoclinic semiconductor with really high, at low temperature, very high mobilities. And it's also topological insulator and so on. So I saw the paper and I thought, well, that could be interesting for plasmons, but I didn't think even further. So I had a postdoc who was very interested in that, Xu Shen. She contacted the group, and a few weeks later we had the platelets. And we saw polaritons after a while, but what was really surprising is, if you look at these images, these were the platelets that we placed on silicon oxide on gold. We did that to enhance the propagation length, but I don't have time to talk about that. If you're interested, please look into the paper. And then we see these platelets here. They have a very characteristic shape. And then we see polariton fringes here, all the way from 1 terahertz to about 6 terahertz. But we found these fringes not at all edges. So we saw them, for example, here, right? And they scale very nicely, or this frequency. That's what we expect for a polariton. But then at this edge here, we barely saw them. So that indicated already, OK, that is probably hyperbolic or elliptical. So here we don't see anything. So we were really very excited. Maybe before I continue, let me say one word to the setup. So the setup is a monochromatic imaging setup. So it's based on a NEOS-spec setup, of course. But then we use a gas laser, actually. We don't use TDS. So this is a CO2 laser that pumps some gases, and then we get terahertz radiation. We have about 5 lines, up to 100 milliwatts. That's a really powerful laser. There are very few groups who have this type of setups. I have to say this laser was bought once, built by Coherent, but they don't even know anymore that they built it. So I think I'm the only one in the world who has that in combination with a s-SNOM. But in the end, it's very similar to an Edinburgh system, so it's a classical gas laser. And then we use interferometric detection as usual, but we operate it in synthetic holography mode. If you're interested, there are some papers on that. As also Miriam mentioned it, they're also measuring in this synthetic holography mode. Because at terahertz frequencies, pseudo-heterodyne is a little bit more tricky because the mirror vibration amplitude would be, well, it's in the range of 20% of the wavelengths. And if we operate with 100 micrometer, that's huge amplitudes. So here we just have the stage. While scanning, we just let it linearly run. And then we get kind of synthetic holograms, and which by digital holography processing, then we can turn into amplitude and phase images. But don't want to talk about that. So to really learn more about that and to see really the iso-frequency surface, what we did is we take one of these platelets, we use focused ion beam to make a disk, and then we scan that, because that way we can get reflection in all directions, right? As we did with formerly with the MOS3. We get this here, and then we do some image processing, Fourier transform, and we see here beautifully this elliptical iso-frequency surface that indicates these are not hyperbolic, but elliptical polaritons. Now, what was strange, what we really didn't understand is there are 2 semi-axes, right? And one of these semi-axes of this ellipsoid is aligned with this edge here, but then the other one not. So why do these platelets grow so strongly, and what is the relation between lattice, conduction properties, and these iso-frequency surfaces? And nobody really knew what these materials exactly are, what the crystal structure is, how they're oriented. So what we did is we took one of these platelets, we took focused ion beam, and we extracted a lamella, and we did a TEM in this lamella. We went to literature, databases, and we could match actually the crystal lattice to the TEM image here. And from that, we could find out that's a monoclinic structure indeed. But the unit cell vector B that is orthogonal to non-orthogonal vectors is actually in plane. So that's now a top surface view. And what you see here is a projection of the unit cell onto the surface of the platelets. And now we see that all these projected unit vectors are orthogonal. And in principle, we have an in-plane orthorhombic or rectangular system. And that explains, and it also is very well aligned with these semi-axes of the ellipsoid. And that explains why we observe elliptical modes and not shear polaritons and so on. Now, having that, we can do DFT. And from DFT, we found out that we have a parabolic band structure with a band minimum at the gamma point. So that behaves very nicely as a metal. And that's the last slide that I want to show. So by now modeling this here via an anisotropic permittivity tensor, assuming a Drude model, and knowing the carrier density from Hall measurements, we can extract actually the in-plane effective masses is exactly in this direction. I think that's a very nice application, which has nothing to do with photonics. If one is interested in effective masses, that would be really tricky to measure. Terahertz spectroscopy is a powerful tool, but on this scale, obviously hard to do. But with this polariton interferometry, we can actually get masses. They are about 2 to 3 times different in the 2 different directions, and they fit perfectly or very well together with DFT calculations. So that's an interesting application here. So Chairman is signing up, so I think I have to finish. Just want to thank the people. Oops. So the terahertz work on the platelets was done by Xu Shen. She's now in Shanghai, and the Eugenio Calandrini was a postdoc with me, and he did the work essentially on HBN. And with that, I'm at the end, and thank you for your attention.
Thank you very much for the nice talk. So we have time for 1 to 2 questions. Any? Yeah.
Yeah, thanks, Rainer, for the great results and nice talk. So I have a question about the HPN work. Was that on isotopically pure HPN?
No, no, this was CBD grown.
And can you potentially do that with CBD and then improve the results? Because you could feed it, right?
That's a good question. We would need to ask Andrea Ferrari, but I think he's probably not here anymore. So I cannot tell you, no. But I guess not. I guess it's just a normal composition regarding isotopes. But that's what I suspect.
Any more questions from our audience? Actually, I have a quick question. So, a follow-up question. So, what's the domain size of the poly HBN?
What's the
domain size?
The domain size was in the range of hundreds of nanometers.
How would that affect the polariton you measured?
That's a very good question. As I said, that was one of the very few materials that we got where we saw these polaritons. In principle, we would need to make a follow-up study, seeing whether these polaritonic patterns, these random patterns, somehow scale with defect density. So we tried with machine learning to see whether from the patterns we can learn something about the distribution of these defects. But it's a bit of a tedious work, so we did not so far follow up on this, so I cannot tell you. But it would be definitely interesting to study.